Hello everyone, my name is Shahab from the University of Sheffield, United Kingdom, and today I'll be presenting some of the recent work we have done on state of charge estimation for lithium-ion battery cells. So the battery energy storage has been a great solution for many different power applications over the recent years, and the emergence of lithium-ion battery cell chemistry in particular has given rise to a new level of portability for power applications. Now, this is due to many different properties of these battery cells, and having a higher energy density and power density compared to other cell chemistries is one of the virtues of these battery cells. And we have seen these lithium-ion battery cells in various different applications, such as electric and hybrid electric vehicles, portable electronic devices, and etc. Here you can see an example of a lithium-ion battery pack integrated into a Nissan Leaf for electric vehicle applications. Now, to be able to increase the uptake of lithium-ion battery cells in future power applications, it is important to overcome a number of challenges on the way. And one of the main challenges is the estimation of SOC, or state of charge, in real time. There are a large number of researches conducted on SOC estimation, and they are mostly based on the standard Coulomb counting method, open circuit voltage based methods, and the indirect or model based methods. Now, the problem is for lithium-ion iron phosphate battery variation of lithium-ion battery chemistry. The open circuit voltage obtained across the usable range of SOC range of 20 to 80% is fairly flat, which will introduce large uncertainties into our SOC predictions. So therefore we need more accurate and more robust estimators for this particular variation of lithium-ion battery chemistry. So our technical solution, here is an overview of the proposed structure for the SOC estimator for LFP, or lithium-ion iron phosphate battery cells. So first we characterize our battery cell using a suitable battery model, where we are able to capture the dynamics of the battery cell under operation. Then we apply an online system identification technique based on Kalman Filter to identify our model parameters and estimate the model states in real time. The next bit where the contribution of this paper is a separated Kalman Filter framework for SOC estimation, where we can take our modeling uncertainties into account and produce a more stable SOC estimate. And finally, the SOC estimate is fed into a function describing the relationship between OCV, or open circuit voltage, and SOC. So here is a circuit diagram of the battery model used in this work. It is a second order equivalent circuit model, or Randle's model, where we represent the series resistance of the battery cell using a series resistor known as RS. And we use two series connected RC branches to describe the long and short time constant reactions that occur in the battery cell. And so these reactions, the long time constant reactions, are associated with the diffusion resistance and the diffusion capacitance, whereas the short time constant reactions are mainly caused by the double layer effect and the charge transfer resistance of the electrodes. Okay, so in order to validate the battery model and the proposed SOC estimation technique in this work, we did some testing on an LFP cell with a nominal voltage of 3.2 volts and a nominal capacity of 3.3 amp hour. So we did two separate current profiles on these on the test battery cell. The first one is a pulsed current profile for OCV extraction, where the battery is first discharged to 0% SOC or the lower voltage threshold of 2 volts, and then recharged back to 100% SOC using a constant current, constant voltage method. Now, after allowing the battery to rest for 1 hour, the first OCV was recorded at 100% SOC. Then the battery was discharged in steps of 10% SOC following a 1 hour relaxation period, which enabled us to establish an OCV measurement at each SOC step. So the same procedure is repeated for a charge period. So the battery is charged up in steps of 10% SOC, and the OCV is extracted after 1 hour relaxation. The second current profile is a self-designed pulse profile for cell dynamic excitation of the cell and for the verification of the SOC estimation technique. So on the right you can see one sequence of the self-designed pulse profile. So this profile is repeatedly applied to the cell until it hits the lower voltage threshold of 2 volts. The testing equipment involved in testing the battery cell features a multi-channel Mako 4000 series battery tester, which has great sensor accuracies. So therefore, in this work, we have taken the integral of current measured by the current sensors on the Mako battery tester to be a true representative of our SOC in this work. Now, the batteries are tested at various temperatures. So in order to keep a static temperature profile, we have built a thermal chamber which consists of essentially a fridge freezer with a controller on top. The measurements are taken by a PC which also controls the Mako tester as well. So here is a definition for SOC in discrete form, where SK is the SOC estimate at the current time step, and eta is the coulombic efficiency for the test cell, which is experimentally determined to be 0.98 in this case. Also, CAS is the ampere second capacity of the test cell at the test temperature, and TS is the sampling time. So after applying the test cell with the OCV testing profile, we have obtained a relationship for the OCV versus SOC at different temperatures. And we have expressed that as an 8th order polynomial function. So on left you can see the OCV curves obtained for the LFP test cell. It is apparent that between 20% and 80% SOC, the OCV curve obtained is fairly flat, and also we can see on the right that due to temperature variations, there is a non-linearity existing in the OCV and SOC relationship. So once we've got our data set, we need to identify our model parameters. So we have used the extended Kalman filter, which is a non-linear alternative to the original Kalman filter, to do so. we have implemented the EKF in a parallel or dual fashion, where the states and the parameters are estimated simultaneously. So the way the algorithm works is that we make some predictions about our model parameters and states based on the prior knowledge of the system, and we try to update our predictions and correct our predictions based on the new measurements coming from the voltage and the current sensors. Okay, so here's the structure of the proposed SOC estimator. So the way the algorithm works is that we have designed a third separate EKF for SOC estimation alone. So in this way, we are able to take into account all the modeling uncertainties and the nonlinearities introduced into our model by the OCV and SOC relationship, and we estimate our process and measurement noise covariance in real time. So in that way we can condition our noise covariance matrices for a better and more stable SOC estimation. Okay, so here is some results to validate our battery model and the dual EKF battery parameterization in time domain. We can see that the obtained cell voltage from the battery model is in good agreement with the actual voltage of the cell under the self-designed pulse profile testing regime. And we can see that the modeling error in most cases is between plus and minus 10 millivolts, which shows the robustness of the EKF battery identification technique. Here we compare the SOC achieved using the ordinary dual EKF and the proposed EKF estimator in this work. On left we can see that the SOC obtained using the dual EKF suffers from instabilities around the 30 to 50% SOC range, and outside that range also the SOC is suffering from large inaccuracies. Whereas the proposed technique on the right shows that by taking into account the modeling uncertainties and the nonlinearities of the OCV and SOC relationship, we can produce a more stable and accurate SOC across the whole state of charge range for the battery cell. Now, to further our investigation and show the excellent convergence of the SOC estimator in this work, we have set the initial values for the separate EKF to 40% and 80% instead of the true 100% value. As you can see on left, the filter is capable of converging to the real or true SOC in less than 1 hour time for 80% initial SOC, and just over an hour for the 40% SOC. So this proves the convergence and tracking capability of the proposed technique in this work. Okay, so to conclude this presentation, we said that there's an increasing trend in LFP battery powered devices, and we also said that one of the main challenges with these battery chemistries is the state of charge estimation. So this is due to the fairly flat OCV curves obtained within the usable SOC range of 20 to 80% for these battery cells. And we said that this will lead to large inaccuracies and instabilities in the SOC estimation within this SOC range. So we proposed a more robust estimation technique based on the original dual EKF, where we designed a third filter with real-time noise covariance matrices predictions, which gave us the ability to capture those nonlinearities in the OCV versus SOC relationship and reduce the modeling uncertainties. Finally, we tested the proposed algorithm on an LFP cell of nominal capacity 3.3 amp hour. The results showed great tracking capability and convergence capability of the algorithm, which is great for real-time online applications. Okay, thank you very much for listening. I hope you enjoyed this virtual presentation, and hopefully Dr. Gladwin will be able to answer any questions you may have. Thank you.